Good evening, friends. My name is Gautam Das. We'll continue with the stability of the carbocation. This will be the level 2 one. But before going to the level 2, actually, we'll do a few questions, which will be the revision of the first one, which was uploaded before in the earlier video. Like suppose you have suppose you are being asked to arrange this in order of again decreasing stability. Is very simple. In D there is plus I effect as well as hyperconjugation. In all these three from A to C there are minus I effect. In all these three there are minus I effect. So obviously each of these C, B, A will be less stable than D. That we already know. This is very simple. And if we consider the minus I effect, decreasing order of minus I effect, minus nitro greater than chlorine. So more is the minus I effect. We have already discussed in the last video. You already know that more is the minus I effect, more electrons, more unstable or less stable will be the carbocation. So here the stability order is pretty simple, which is D, C, B, A. D plus I effect as well as hyperconjugation effect, 2 alpha hydrogen atom. And here the minus I effects are operating. Minus I effect is least in chlorine. So among the three, this is more stable than chlorine, than nitro is stable by minus I effect. If I consider another question, this is also quite simple. Suppose if we consider these three, again A, B, C, and you have to arrange them in order of again decreasing stability. This is also quite simple. This is the only one, the C, where there is a plus I effect, and we also can consider hyperconjugation. If hyperconjugation, obviously more if it is inductive way, that we have discussed in details in the earlier one. Now remember this B1, this is not allylic. The this positive charge is not immediately adjacent to the carbon atom containing double bond. So here obviously minus I effect will be operating. If you consider the hybridization of this carbon atom, this is sp2 and this is sp. Okay. Now overall effect for A and B, there will be minus effect, electron withdrawing effect, and overall effect for C will be plus I effect. This is a competition with plus I and minus comparison with minus I. Now we already know one thing more, S character, part of bonding, which we have already discussed in the last video. More S character, that is more electronegative carbon. That means more powerful minus I effect. More minus I effect means obviously less stable carbocation. The reason we already know. So obviously the stability order for this particular question, will be C plus I effect, both B and A minus I effect, but minus I is more in A than in B, more minus I effect, less stable. So it is C, B and A. I'm giving you another question which is nothing but application of whatever we have done in the last video. Now, if you look at this particular question, it's already known to you. Now, obviously, you have to arrange them in order of decreasing stability, descending order. Now, if you consider this carbocation, these two alpha hydrocarbon atom are common in each of them. So each of them has this 4 alpha hydrogen atom because of this 2 that is common in each of them. So we don't have to consider this. Now if I consider this carbon atom, if we consider this carbon atom, let us consider this figure. Nothing. This has no alpha hydrogen atom. So here in this portion, this has no alpha hydrogen atom. So there will be no hyperconjugation here. This portion, if I just for the purpose of understanding, if I just name it as A and B portion, this A and B portion, they are common. If I consider this E carbon, A and B and this E carbon, in each of them they are devoid of any, E carbon is devoid of any alpha hydrogen atom, no alpha hydrogen atom here, so no hyperconjugation. So this portion, this particular portion is only exhibiting plus I effect. So is this and so is this, and we already know the plus I effect of deuterium is greater than hydrogen, which for which the inductive effect is actually 0. It is the reference scale. So obviously here inductive effect will be the predominant factor, because for A and B carbon there are 4 alpha for each of the cases, so we cannot compare by that. So the plus I effect, by plus I effect of D and CD3 and CH3, we have to compare the stability. So stability order will be maximum here, because there are 3 CD3 groups, then 3 where there are 2 CD3 groups and 1 CH3, then 2, 1 CD3 group, 2 CH3, and then 1 where they're all CD3. So it will be simply 4, 3, 2, 1. All these questions, whatever we have done, these are not difficult at all, and these are nothing but revision of the earlier discussions which we have. I think you would have done on your own, pausing the video without looking at the answer. You would be able to answer most of this. These are of actually of NEET level or JEE mains level and so on and so on. Now if we go to some before giving you some decreasing order of stability as such, without considering a question. Now there is one thing which you're supposed to know. Actually, this is something which is data based. You have to know. It's not that you cannot predict. If you don't know, you cannot predict in the exam hall. You have to know actually. Now we know one thing, that we have discussed one thing, that resonance effect is greater than hyperconjugation, which in turn is greater than inductivity. So far as we have considered, we have not considered aromatic, or we have not considered dancing resonance yet. So this we already know. So if I consider, suppose, benzyl carbocation, and if I consider tertiary butyl carbocation, this is tertiary butyl carbocation, which is obviously a 3 degree carbocation. Now, tertiary butyl carbocation, there are 3 alpha carbons, so 9 alpha hydrogen atom. So hyperconjugation is there because of 9 alpha hydrogen atom, as well as there is plus I effect exhibited from the 3 methyl groups, and there is one plus R effect exhibited by phenyl group. And normally, what is the normal sequence? Normally, we should go for this thing, that this benzyl carbocation should be more stable than benzyl carbocation, but it's not the case. Actually, stability order, if we consider, benzyl carbocation is more stable than, slightly, but still it is more stable than benzyl carbocation, and that is very important. This is a database question, that's why this is important for JEE advanced level. But that means, don't confuse this with this thing, that doesn't mean that all 3 degree carbocation will be more stable than benzyl carbocation. No, it's only for tertiary butyl carbocation, because it's actually, forget about tertiary butyl carbocation, it is only for 9 alpha hydrogen atom system. So if we consider, suppose, another 3 degree carbocation like this, if we consider another 3 degree, 1, 2, 3, 4, 5 like this. Now here, this 3, 6, 8, so there are 8 alpha hydrogen atoms. So here also there will be hyperconjugation, here also there will be plus I effect by 2 methyl and 1 ethyl groups. Although the plus I effect may be more here than here, but actually hyperconjugation predominates of plus I effect, and you will only consider plus I effect when all other factors are same. That means resonance, hyperconjugation are same. Then only you will consider plus I effect. Otherwise, you don't have to consider. So this is less stable than benzyl carbocation. This you have to know. Actually, this is something database question. This comes from something called hydride ion affinity. This is some values we have to know. But you simply remember, for 9 alpha hydrogen, if there is 9 alpha hydrogen atom, then that carbocation is more stable. So this is 3 degree. This is also 3 degree carbocation, but not 9 alpha. It has less alpha hydrogen atom is less than 9 alpha. So this thing you have to remember. This is quite important, and it often comes because often it is considered as an exception. If you think like that, it is an exception, but actually you should remember the 9 alpha hydrogen, the overall effect, overall electron releasing effect, because of the hyperconjugation due to 9 alpha hydrogen atom, as well as plus I effect of 3 methyl groups, is more electron releasing than the plus I effect exerted by 1 phenyl group. But this will be even less stable than diphenyl methyl carbocation, where there are 2 plus R effect. So knowing this thing, let's have a generalized stability order of carbocation, of simple thing, so stability order of carbocation. Now, if we consider this is the decreasing stability of carbocation. Now here this is resonance plus R effect. This is triphenyl methyl carbocation. This is biphenyl methyl carbocation. Then comes, this is the database exception I'm talking about. Then comes the tertiary butyl carbocation, which is more stable than benzyl carbocation. You have to remember, you have to be very careful about this one, this portion, very careful. Then the allyl, this is benzyl. Then comes allyl. Again, resonance. Here also we have resonance, more resonancing structures involved here than here. Then comes 3 degree alkyl carbocation. Now, as already discussed, it is other than the tertiary butyl one. Tertiary butyl carbocation having 9 alpha hydrogen atoms. Then come 2 degree alkyl carbocation. Then comes 1 degree alkyl carbocation. This we all know because of the plus I effect. Here, the plus I effect is decreasing from here to here. Here the resonance effect is, plus I effect is decreasing. Here is the same thing. Here this is the exceptional part which you have to know. Then comes methyl carbocation, and then comes this, after this methyl carbocation, then comes vinyl carbocation. Then comes phenyl carbocation, and then comes, this is actually ethynyl carbocation, which you consider as alkynyl carbocation suppose. Here also there is some fallacy which you have to remember. Now, up to from here to here, if you consider from here to here, this from here to here, and if you consider from here to here, there is hybridization is important factor, because up to this we have typically sp2 carbon. The carbocation is sp2 carbocation. This carbon atom is sp2 carbon. Okay. Now here, this we have discussed in the last class. Here it is sp hybridized, but here it is sp2. This we'll discuss with diagram. Here it is again sp. Now, if I consider just take this vinyl and ethynyl, their stability can simply be explained. Vinyl structure wise, we have seen in the last class. This ethynyl, if you want to see the structure, this is one pi bond, this is another pi bond, and this is the vacant sp orbital which accommodate the positive charge. So in no way this 2 pi, suppose this is along x-axis, so this, suppose this is 2 py, and suppose these are 2pz. This is a sp2 vacant orbital. So sp2 vacant orbital. Sp vacant orbital. As we have seen in the case of vinyl carbocation, this is sp orbital. So why vinyl is more stable than alkynyl, that can be simply explained once we know this hybridization that can be simply explained. Both are sp. But if you look at this carbon is sp2 while this carbon is sp. So this carbon will exert more minus I effect than this carbon. That's why stability wise this is more than this. But if we consider phenyl carbocation, if we actually look at the phenyl carbocation structure, for that if we consider suppose an halobenzene, this is what, sp2 hybridized carbon. Everybody knows that. So when it is leaving, suppose it is leaving by some means or other, by how we are not interested at this moment. So we'll get something like this. So this is a vacant sp2 orbital which is accommodating the positive charge. So if we consider the aromatic ring which is perpendicular to the skeleton, this is the aromatic ring which is the delocalized perpendicular skeleton, while sp2 which bear the positive charge that remains in the plane of the ring. So this is very unstable because it cannot be stabilized by this. But it is more stable, again from the hydride affinity we came to this thing, it is more stable than this sp. Actually if you consider the hybridization factor only, then phenyl should be somewhere here, but this is the actual order. Although this is sp2 and both of this carbon atom, here the carbon atom which is accommodating the positive charge of the vacant, there is sp2, while in this vinyl and the alkyl it is sp. But still this order, this you have to remember. Just remember there are two fallacy in it which you have to, this is database thing. One is this tertiary butyl greater than benzyl, then allyl, the normal thing. Then have a 3 degree alkyl, obviously other than tertiary butyl, that's other than 9 alpha hydrogen atom. Then the normal plus I effect, as plus I effect is, if I start from here once more, so here more plus I effect is decreasing, stability is decreasing, then comes this and this is that exceptional part, or because of the 9 alpha and resonance, the difference between that. Then again are two equivalent resonance structure and so and so. Then from here to here the plus I effect is decreasing from tertiary butyl to 1 degree, from 3 degree alkyl to 1 degree alkyl, plus I effect decreasing. Then methyl carbocation. Methyl carbocation is more stable than vinyl carbocation because after all this carbon atom is sp2 hybridized, and from vinyl to ethynyl the stability is decreasing. Just remember from vinyl and ethynyl the hybridization is of the carbon atom according to the positive charge sp, and phenyl it is sp2, but still this order. You just have to remember this order. You have to remember this order actually. Now obviously if you like this video, please press the like button and subscribe to this channel, and it will be better actually if you anyway if you can join the classes. The details are all given at the bottom. Now we'll continue with this in the next video, where we'll do consider some extra stable carbocation, which is actually the level will be a little bit higher than this. And anyway, thank you for watching.